I mean, obviously there's, what did I say? There's 2, 3, 4, 5, 6, 7, 8. There's 8 of you, so 5 people are not here for whatever reasons, and that's okay. If you have to miss for some reason, it's really not a big deal because we're making all kinds of accommodations for the pandemic, obviously. So, I'll do everything that I can to try to make sure that you get the same materials that you would have gotten if you'd been in class. Obviously, it's more difficult to ask questions when you're not in person, though. So we're going to talk first about polarity, and electronegativity is what I really like to cover at this point. Now, polarity is telling us that there is a positive and a negative side to something. So you should have covered that in general chemistry, and we hope that that's something that you can recall easily from general chemistry. Where is the AC setting in here? In the classroom next door, when I was teaching this class, it would drop down to 60, and then it would go back up to 80. And then drop down to 60, and it was just like this the whole time. And I'm concerned that I'm warm, but maybe that's just me. It's not the virus. I don't have anything, okay? So polarity is going to be, we're dealing with things that are polar. Now, when you hear the word polarity, we've got this huge pole that affects us every single day. And are we aware of it? And do you know what it is I'm referring to? The magnetic pole of the Earth, the Earth's magnetic pole. All right, so, north is at the top of it, and then we have south is down at the bottom of the Earth, just like that. And we've got this magnetic field that flows back and forth from the positive to the negative side, and that's what this magnetic field does several things for us. The magnetic field protects us from some of the cosmic rays from the sun, and it also helps to make sure that the center of the Earth stays liquid. And the liquid center of the Earth is a lot of the reason we have the poles where they are. Now, they've shifted over time. But when we talk about this, every time I talk about polarity, I always relate this back to magnets. Because as a kid, I played with magnets a lot. Did you ever play with magnets when you were a kid? Did you ever have a compass and you put it near the magnet, and then you know that the south end of the magnet gets attracted to the north end of the compass, you see, because opposites attract. So when we're talking about magnets, and we've got a magnet that is a north and south pole magnet, and then we put it next to a compass, which I'm doing a bad job of drawing a compass right now. It's going to take me a little bit to get back in the groove of things. And you may say, well, you weren't back in the groove the other day either when we were doing this last week online. So here's our compass, and we're going to pretend that it spins around right here, and there's a south end of the compass. And so this gets attracted with the opposite poles of the magnetic field. When we're talking about polarity and we're talking about molecules, it's a very, very, very similar concept. The opposite is going to be attracted. Now, the easiest and the most straightforward is to take any binary salt. Now, binary salt would be like sodium chloride. And sodium is, what type of element is sodium? I'm reviewing some things here. What type of element is sodium? We got major types of elements. You look at it on the periodic table, you should be able to tell. It is a alkali metal, actually, first column, alkali earth metal. It is a metal. That's the big key here. It is a metal. Now, sodium is a metal, and look, it's on the left-hand side of the periodic table over here. And then we got chlorine, which is not a metal, so it is a non-metal. Oh, you jumped on top of that one, didn't y'all? So we know that chlorine is a non-metal, and it's over on the right-hand side of the periodic table. So as you've seen on my lecture online, I have this habit of drawing out little periodic tables. And I'm actually not that bad at it. So over on the left-hand side, we've got sodium, which is located right here. And then on the right-hand side, we've got chlorine, which is located somewhere around here, about like that. And this is what we need to know about electronegativity. We look at the periodic table. Electronegativity increases from the left to right. From the left to right. So from left to right across the periodic table, electronegativity increases. So looking at this, we should be able to tell, hey, we got sodium chloride, we got sodium, and we got chlorine. We got a metal and a non-metal. So electronegativity increases as we go from left to right. So which one of these is more electronegative? Chlorine is the more electronegative of the two. So it is more electronegative. And I'm going to say I'm going to write I will write the symbol for an electron for that, and then I'm going to say just negative. That's going to be our abbreviation throughout this class when we're talking about electronegativity. So you can kind of, you don't have to write out electronegativity every single time. You can just say eneg. Okay, so chlorine is more electronegative because it's further to the right of the periodic table. That's how the trend in electronegativity works. So what if I go from the right to the left? It decreases. Yes, the opposite is true. That is very good. Now we also go in another direction, and I didn't mean to draw that little mark, so I'll erase that. If we go from the bottom to the top, something else happens with electronegativity. It increases as we go from the bottom to the top. A very large part of organic chemistry is knowing this rule. I cannot express to you how important it is to remember this at all times. Okay? Now, with that being said, we do have a column over here that is a very special column. It's right here. And what are those? Those are noble gases. All right, so they're not electronegative. And you know what I just did? I started writing the word out, and I told you we were going to abbreviate it. They're not, and they do have some electronegativity to them, but they typically don't fall into it. So knowing that as we go from left to right across the periodic table, it increases in electronegativity. As we go from bottom to the top in the periodic table, it increases in electronegativity. And then I'm going to ask you this question. What is the most electronegative element on the periodic table? Fluorine. It is fluorine. So fluorine is the most electronegative element here. It's the greatest in electronegativity. Fluorine is the most electronegative element on the periodic table. What is the least electronegative? Say it again. Francium. Francium. It is the least electronegative. Now, I'm going to talk a little bit about politics of foreign countries in World War II. I am. That's what's funny. I always remember this because France, they pretty much, they gave up. I mean, I'm sorry if you're French, but if you remember your World War II history, the French, they're like, oh, yeah, oh, okay, and they kind of just gave up. So we had to go over there. We did, you know what's crazy? They did the same thing in World War I. It's like they just couldn't get it together. So francium is the least electronegative. Being less electronegative means you're more likely to lose an electron. Francium loses electrons more than anything else on the periodic table. Everything on the periodic table takes electrons from francium. Just like the French. They take their land away. The U.S. has to go in and take it back. But there is an americium. Let's see, where is that one on? They don't have, there it is, AM, number 95 here, americium. So that's a radioactive element. But, it's named for America, right? Yeah, America. All right. Anyway, so we come in and save the day. But there's no relationship between the element of americium and francium on the periodic table. Just, I like to point out that there is one name for us, too. Okay, so we're talking about electronegativity. Now, that gives this molecule, which is actually an ionic compound. This is an ionic compound. It's ionically bonded because sodium has a positive charge and chlorine has a negative charge. And so we have what's called a dipole moment, and it looks like this when you're drawing the molecule. This is the dipole moment. Now, that arrow always points to the negative side. So I'm going to write the negative over here. Well, that was a bad job of that. Got a little negative over here. And the positive side is always going to be the side that has the plus on it. You see how we put a plus on the arrow? That helps us to remember which side is going to be the positive side. So sodium chloride is a polar molecule, and it looks like that. Now let's go for another polar. Good job. Let's go for another polar molecule up here that we're quite familiar with. It's one of the first compounds you probably learned how to name, and that is the good old dihydrogen monoxide. Very dangerous stuff. Do you know that this has been found in the bloodstream of every person who has ever overdosed? It has. It's distressing. Okay. Actually, it's been found in the bloodstream of every person who has ever died. Yep. There was actually a little thing that went around in the 80s, and it's called banned dihydrogen monoxide. Like, oh, yeah, that's bad stuff, dihydrogen monoxide. It's going to mess everybody up. We've got to get rid of it. All right, so dihydrogen monoxide. Let's draw this out. Let's go to Lewis structure. Make sure we remember how to do all this together. Okay, so we're going to draw a Lewis structure of dihydrogen monoxide. Lewis structure, first thing we know, we'll look at this compound, we'll say H2O. Okay, and I know that you've all seen this before, but it's worth repeating it, just to make sure everybody's reviewing it in your mind, refreshing those cobwebs, right? All right, so first off, we look at this and we say we only have one oxygen, we've got two hydrogens. So we got to have a central atom in this, so oxygen's going to go in the center. So we'll put oxygen in the center just like that. And we know it's going to have at least one bond to each of these hydrogens. And that's very good because hydrogen, how many bonds can hydrogen make? One. It will never, ever, 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 ever have two bonds. It cannot. It does not. And it shall not. So if you ever draw a structure and you wind up with a double bonded hydrogen, you're wrong. And I think I'll just go ahead and give you an F on that test. Okay, so keep that in mind. All right, so we've got oxygen and hydrogen. We put it in the center just like that. Now, this is covalently bonded. We know this is covalently bonded, whereas sodium chloride is ionically bonded because we have a metal and a nonmetal, but hydrogen and oxygen are both nonmetals. They are a gas at room temperature when they're in their elemental form. It tells us a lot about them, so they're going to be nonmetals. So we need to count out our electrons at this point. So we know oxygen, looking at the periodic table, we'll count from the left-hand side, lithium, beryllium, boron, carbon, nitrogen, oxygen. 1, 2, 3, 4, 5, 6. So we know oxygen, looking at the periodic table, is going to give us 6 electrons. That's where that number came from. If you were looking at the work from the work, and you're like, well, where did the number come from? Well, that's where it comes from. And we know that hydrogen would have exactly 1 electron, but we have 2 of them. So we got 2 electrons from hydrogen, which gives us a total of 8 electrons. Well, now we've got the 2 bonds, right? We've got these 2 bonds that take place here, and each of these are shared pairs of electrons, so that gives us a total of 4 electrons that are used from bonding. And that gives us 4 electrons left over. Oxygen has to have how many?
8.
How many does hydrogen need? 2. Hydrogen needs 2, oxygen needs 8. Hydrogen is happy. See, the next step when we're drawing a Lewis structure is we want to put an octet on all of the terminal atoms. Winter Park, Florida. Oh, I can't answer this right now. I actually know who that is. But anyways, that may have just cost me some money, just to let you know. So, hydrogen, typically when we draw a molecule, the terminal atoms, we will complete their octet. Okay? Hydrogen doesn't need an octet, so it's full with just 2. We see that a lot in organic chemistry because most of the things in organic chemistry are going to be carbon and hydrogen. So always remember that. Oxygen has to have 8, so I'm going to throw in a pair of electrons just like that. And that gives us 4 non-bonding electrons. And that's going to give us a total of 0 left over. So we know that that's the structure. And we knew this going into the class because you learned this when you were in 8th grade, probably. Who took chemistry in 8th grade? I took chemistry in 8th grade. Funny story about my chemistry in 8th grade. My chemistry teacher in 8th grade gave us all a pretest the very first day of class. I was kind of a nerd. And got the test, and it had like something from every chapter through the entire year. And I made 100 on it. And he said, Mr. Hurt, because that's what he called me, Mr. Hurt, you got a perfect score on the pretest for chemistry. I'm like, okay. He said, I'm going to tell you what I'm going to do. I said, what's that? And he said, you're just going to get 100 on everything. I'm going to use yours as the key for the rest of the year, which really put a lot of pressure on me. And he did. every time we had a test, of course I took all my tests like I was supposed to, he would use my test to be the key. And so at the end of the year, I had a 100 average in chemistry in 8th grade. I don't know that I really deserved it because I'm sure I missed some things. But that was his idea of whatever. I don't know, motivation. I don't know how you would say that. All right, so we look at this molecule and we got to look at it and we say, all right, we draw it like this and see. You're at a disadvantage because I can zoom it in on mine, and then it's up here. It's not zoomed, but I'm sorry. This doesn't work. Notability is what I use when I'm lecturing from my office, and I can zoom it, and it zooms on the screen so you can see the zooming. But here we go. We're looking at this molecule, and we're going to say, okay, we need to know if this is a polar molecule or not. But we all know already that water is a polar molecule. And if we draw it like this, and we have our non-bonding Lewis dots are on the top and the bottom, and this is where I'm kicking myself because I forgot my model kit today. After I talked so much about how much I like my model kit, I left it. But this would have been crucial. When we draw this out like this, it looks like, well, everything balances out because we've got just as much electrons going in this direction as we have going in this direction, right? When we look at the number of electrons there. And we've got just as much of a change in electronegativity from oxygen to hydrogen as we have from oxygen to hydrogen the other way. So it's like a tug of war, and they're all pulling opposite each other, and they're exactly the same power, so that this looks like this is not a polar molecule. But what we've got to remember is we've got to step back and think of it in 3 dimensions, because we could easily draw this molecule again, and I'm going to draw it like this. Same idea. We space the electrons around at right angles to each other. But if we draw it like this, we can see, and that was small for you guys. Let me zoom back out on that. I'll draw it again. That's a little small. But if we draw it like this and we put the electrons here, we're not in any kind of violation because we know that things that are alike don't like to be next to each other. And so they're going to try to be as far apart as they can. That's called valence shell electron pair repulsion, VESPR, V-S-E-P-R. I pointed that out in the previous lecture stuff. So we've got this little cloud of electrons over here and a little cloud of electrons over here, and they repel each other. So we look at this and we can figure out that our dipole moment is going to be like this. Why is it going to be like that? Remember, down here, we go from the positive side towards the negative side. Well, can you get any more negative than an electron? You cannot get more negative than an electron when you're talking about chemistry. Well, we'll look at this bond between the hydrogen and the oxygen here, and we'll see that the hydrogen to the oxygen bond is a disparity. This is a polar. There's a dipole moment associated with it, and that dipole moment goes in, it's positive more towards the hydrogen, negative more towards the oxygen. So all that goes together. You took physics before? Who's already had physics? Okay. There's this thing in physics called vector addition. Okay. You don't know what vector addition is? No. Okay.
Why don't I remember it?
Well, vector addition is like I'm trying to think of a really good way to illustrate this that doesn't involve guns. Okay. All right. No, it's just I grew up on a farm, so I've shot plenty of animals. I'm sorry. I don't want anybody upset over this. All right. So if we think about let's football. That's a good one. Football's okay, right? So you got this guy, and he's running, right? And he's running this direction, and he's going like 5 meters per second. I'm not going to put the math. I'm kidding about the math. I'm not going to do math. But say this guy here, and he's running in this direction, and then you got another guy that's running, and they're going to collide with each other, right? And he's going in this direction. They're going to mash together, and then they're going to wind up traveling in a similar direction because the two forces cancel each other out. You see, so this guy's going this way, and this guy's going this way, and so the resulting direction is going to wind up being this direction, because they hit together and then they continue to travel. Now, it can vary depending on which guy's running the fastest and which one's the biggest. Same thing with electronegativity. It's going to vary depending on which atom is more electronegative, which one's less electronegative, and what direction it is and what angle, and that sort of thing. But it's like vector addition in physics, so you can look that up. There's a really good YouTube video about it.
Like elastic and inelastic collision?
Yep, that kind of stuff. Yeah. And so you ever seen two cars collide, like you watch NASCAR? I don't watch NASCAR, but if you watch NASCAR and they hit, they always wind up going, anyways, so you get the idea. So anyway, that's how the dipole moment there would take place. So let's look at another one. Let's look at, trying to think of a good one. Oh, here we go. C2H2Cl2. C2H2Cl2. Now, this is dichloroethene. Okay, it's called dichloroethene. Dichloro, because it has two chlorines. So we name it dichloroethene. Oops. ETHENE. And the reason it's ethene is there's a double bond in this, and I'm going to show you the double bond here. So the carbons are going to wind up double bonded to each other, and then we're going to have a chlorine on this carbon just like this. We'll have a chlorine over here on this carbon just like this. Okay, so that's dichloroethene. Now, I did not denote numerically the location of the chlorines, but we'll get that in a moment. But I want us to realize that there's this thing called structural isomers. Structural isomers have the same formula, but they don't have the same structure. So that's a structural isomer. It will have the same formula, but it won't have the same structure. Okay? So we'll look at this one, and this would fall into the family of dichloroethene. And we have the double bonded carbons, that's the ethene part. And then we've got chlorine on each one of those, just like that. We can look at this and we can make a determination that there is some amount of polarity to this molecule, and it goes in that direction. Because chlorines are more polar, or more electronegative, than hydrogens, right? We can agree with that. When we look at it on the periodic table, we can tell. That is just one way that dichloroethene can form. Each chlorine is on a different carbon. Okay? There is another way that this can form, and I'm going to draw it to the side here. And we're going to draw it with both chlorines on one end. Okay? Looking at this, where would my dipole moment be? Where would the dipole be? They go right down the double bond. And which way does it point? Towards the chlorine side. So the question I have for you is comparing these two, and I'm not going to get into the specifics of naming these because we'll be doing plenty of that coming up. I just want you to start conceptualizing some things here. We can see that the side with all the chlorines is going to be more electronegative. So my question is, which of these is more polar? Which of these two would have more polarity to it? It is the one on the right. Can you justify that?
I never really understood it. I just think of it as being, if it's even, it's non-polar, if it's not polar.
I mean, that's it. If it's symmetrical, it's, yeah. But see, both of these are non-symmetrical because if we split this down the middle, double bonds don't twist. So you're not going to wind up with this chlorine spinning around and being on the bottom. So if you split this down the middle, you've got a negative side up here at the top. Well, let me do this where whoever has to watch this later. So if I split this right down the middle, I have a negative side that's on the top, and then I have a more positive side on the bottom. And that's where we drew that dipole moment there. So this makes sense. All right, and that over here, and using that same idea, this side is more negative than this side, and that's why we drew the dipole there. But which one of these, so this would be kind of like the split there. The one on the right, the one that's written in blue, is more polar because what is a double bond made up of? I'll highlight that little section right there. What is a double bond made up of? What? Yes, a pi and a sigma bond. And what are those bonds made out of? What makes a bond in organic chemistry? Electrons. Shared electrons. Now, who understands anything about electricity? Inside the wall, we have copper wires, right? And electrons move down those copper wires. Because electrons move and they flow according to a change in charge. So when we have this double bond that's taking place here, this double bond right here in the middle, we've got 4 electrons in that region, in that double bond. We also have 4 electrons here, right? Now electrons can transfer charges, just like getting shocked from an electrical current. Since we have a positive side over here, and then we go across the electron bridge to this negative side, it can draw more of the charge. And so the one on the right is more polar than the one on the left. Because if we go from hydrogen to chlorine here, we go through a carbon. Right, and that stinks. So if I go from hydrogen to chlorine here, we're moving through a carbon. But if we go from hydrogen to chlorine here, we're going through an electron bridge, which allows it to pull more of the charge. And so that makes this, so it's more than just the actual elements themselves, it's the quality of what takes place in between those elements. And these electrons electricity, they let the charge flow. And that's a big, huge deal. Okay, now I've pretty much covered all I wanted with that part of it. And then, of course, my computer logged me out over here. Let's get that back in. Any questions? Okay, no questions? All right, how about you? Guess what? You're not here. So. All right, I'm sorry. I mentioned that when I was in high school, I was a bully. Okay. I am reminded of that from time to time because of my sense of humor. Okay, so let's look at this. Boiling point. Now, there is a problem that has been assigned talking about identifying the boiling point of different organic substances by just looking at its structure. Okay, and so we're going to do a little bit of this, but we're not going to determine the numerical value of the boiling point. We're going to determine the trend instead. Okay, so we've got this compound here. It's HBr, which, we'll leave it with that. We're going to take HCl. We'll take HF. And then we're going to have HI. So we've got 4 different substances here. You should be able to identify these from general chemistry as, when this is put in water, what is this? Hydrobromic acid, hydrogen bromide. Put it in water, it's hydrobromic acid. HCl is hydrochloric acid. HF is hydrofluoric acid. And then HI is, that's an uncommon one. That's hydroiodic. Hydroiodic. Which is kind of funny. It always reminds me of this. H3O3. You see, no, that's iodate, excuse me. IO4. This is actually periodate, and so this is actually periodic acid. It's like just occasionally it's an acid. It's not always that. At some point you're going to realize, anyways, you may not. It's a clever chemistry joke, but maybe not. Okay, boiling point estimations. All of these are gases. Okay, we can go ahead and accept that. So if we're looking at them, we're going to say these are all polar, right? Because we have a hydrogen and we have a halogen, and each of these has a dipole moment that looks like this. Goes from the hydrogen to the iodide. Okay? And so there are some factors that take place that we have to consider. We have what's called the dipole-dipole interaction. And that is like whenever, that's like the magnets I was explaining earlier. The positive side lines up with the negative side, etc. And then there's also some things that can take place called hydrogen bonding, and they can't take place here. Hydrogen bonding is another intramolecular forces. And that is the strongest of the intermolecular forces. And then the other one is called, what's it? London dispersion, that's it, yeah. That's the one that's the weakest. Okay, so we'll look at these compounds, and these are all polar. So their predominant intermolecular force is going to be dipole-dipole interaction. Okay? So the way that we could determine which one of these would have the higher boiling point, we're looking at it, we're trying to say which one of these are going to be attracted to themselves. So if we've got a container that's full of each one of these, and then we want to determine which one of these is going to have the highest boiling point, it's going to be the one that has the greatest polarity, because the dipole-dipole interaction is going to be the greatest force here. So which one of these would have the greatest polarity? Yeah, the hydrogen fluoride. That's the greatest polarity. And then the least polarity would be hydroiodic, a hydrogen iodide. Now, if you want to look up the values of electronegativity, the place that I would go to look at that is actually called ptable.com. And on ptable.com, it stands for periodic table, obviously. There's actually a link for a periodic table that shows you all of the values for electronegativity. So you can look these up. I think fluorine is like 4.0, I think, 3.98 or something like that. It's like 4.0. It's the most electronegative. Francium over here is like 0.2. He's a wimp. So you can compare those. But as we see the halogens here, they're going up and down the periodic table, so we can easily determine the polarity by looking at where those are located. Now, let me ask you another question to go along with that, though. Let's see. We have this substance here, which we've already discussed, and we've got this other substance here, which we have not yet discussed. Water. What do you know about water? At room temperature and pressure, what is the most common form of water you'll find? It's going to be a liquid, right? So this is a liquid at room temperature. All right. Does anybody know what this other one's called? Dihydrogen sulfide. A lot of people call it hydrogen sulfide. I mean, because that's just the common name for it. Does anybody know anything about it? It's kind of fun stuff. No. Well, it's a gas at room temperature. You ever broke a stink bomb? The smell of rotten eggs? It's hydrogen sulfide. Very first year I was teaching, some kid thought it was going to be clever. In my chemistry class, he dropped a stink bomb, stepped on it, and the class started smelling. Well, I've been in the lab so much, like, it didn't bother me. So I just went on. And so they're all, like, starting to gag and stuff, and I'm like, we're still going. You know, stuff happens. You know, when y'all did it. So then he started getting stressed out because he realized that I knew who he was, and I was just making him, I was just making all of his friends turn against him, you know, and that's pretty funny. He was a senior, and he told me he was going to run me off before the school year was out, and I said, buddy, I will be here long after you have dropped out, and I didn't realize he was a senior, and he said, well, that shows you because I'm a senior. Well, guess what he did 6 weeks before he graduated? He dropped out. Yep, he wound up going to the penitentiary because he robbed a gas station using nunchucks and ninja stars, like the throwing stars, you know. And that was armed robbery at that point, so he went to the penitentiary. I'm like, idiot, you know. Anyways, great story. I try to tell it often. All right. So why is it water is a liquid at room temperature, whereas hydrogen sulfide is a gas? Water can do something that hydrogen sulfide cannot do. And that's that other intermolecular force, the greatest of the intermolecular forces. It can hydrogen bond. So that can have hydrogen bonds. And this was not. Because in order to hydrogen bond, what elements do you need? One of them's right. One of them's really obvious. Right. For hydrogen bonding, we have to have hydrogen. And we have to have at least one of these others. Oxygen, nitrogen, and one more. Fluorine. So we can hydrogen bond if we have any of those. Water has that, and so it hydrogen bonds. Now, hydrogen bonds, how do they work? Well, let's look at this compound here. And I'm drawing this on the plane as a Lewis structure. But keep in mind, what do we say about those two lone pairs on the oxygen? They're actually going to be in three-dimensional space, spread apart. So if you think of it, when I'm drawing this like this, I always envision these electrons as coming out towards me, and then my bonds between the carbon and the hydrogen going back behind me, behind the paper. I think of it as like I'm looking straight down on it. But that's just how I do it. Because when you're outside of the paper, don't you kind of feel like a god because you're like manipulating everything so you've thought about it before. I hear you. I mean, all right. So anybody know the name of this? All right, this is just propanol. I didn't think anybody would know it. That's okay. Propanol. This is actually called 1-propanol. Actually, that's what it was called up until 1994. They changed the way they name these things, and so the modern naming is propan-1-ol, which is nowhere near as easy to say. Propan-1-ol. The OL tells us there's an alcohol in here. The OH is the alcohol. Okay. This hydrogen bonds propanol. You can dissolve it in water because we've learned this thing: the likes dissolve likes. That's why oil and water don't mix, because water is polar and oil is non-polar. So propanol does in fact dissolve in water, and part of the reason that it dissolves in water is because water has hydrogens and water has oxygens. And so this hydrogen bonding can take place. And it takes place in two directions. One direction, the hydrogen gets attracted in here to the lone pair on the oxygen on the alcohol. And that pulls these two together. Another way that it happens is another water molecule can be over here, and then this hydrogen will get strongly attracted. It's not an actual chemical bond, it's a very strong attraction. And so it'll get attracted to the oxygen from over there. So this happens throughout the whole solution, and this is why alcohols will dissolve in water. There are some alcohols that won't because they're non-polar, but we'll get into that later. But these simple alcohols will dissolve in water as a result of hydrogen bonding, because it actually pulls it apart and it takes it around, and it's like it just mixes in. It's like, hey, you're one of the guys, because water's doing this already, hydrogen bonding with other water. And so it sees this alcohol in here, and it's like, hey, you're one of us. You know, we're cool. Let's hang out together. And so that's why this becomes water soluble, because of the hydrogen bonding that takes place in there. Okay. Also makes it hard to do, very difficult to separate these two. When you're talking about in organic chemistry, we'll go in the lab and we're going to do some what's called a fractional distillation. You ever watch the moonshining shows on the History Channel? All right, those guys are stupid. But you separate alcohol from water by boiling it, because alcohol boils at a lower temperature than water. And so when you boil it, the alcohol boils out first, and it goes out through that copper coil and it cools off. And at the other end, you got the toothless man. He's gathering it up, and he's like, oh, that's some good stuff there, boy. But it's all about the difference in the boiling points. Water stays in here. Now, if you go to the liquor store, which I do not advise this, and you go and you say, I want the strongest, most concentrated alcohol in the bottle that you can sell me. Does anybody know how much alcohol is in there? It's Everclear, and Everclear is 95% alcohol. Well, it's not the same kind. Propanol is rubbing alcohol, but ethanol, 95% ethanol is what it is. The other 5% is water, because water and alcohol hydrogen bond. You can't take all of the water out. You cannot have 100% ethanol just from distillation. If you ever run across a solution and it says it's 100% ethanol, they had to add something into it to remove the water. And usually they will add methanol. Now, what does methanol do if you drink that? It detaches your retina and you go blind. So you don't want to do that.
Isn't that like from moonshine, the first bit that comes out has methanol in it?
Yes, it can. Yes, and that's why that's always thrown away. Mm-hmm. That's always. Of course, I don't moonshine. I just want to get that clear. Yep. And they started adding methanol in because they would add methanol to get it stronger quicker, and then they would try to boil it out, and then it just didn't all boil out too. Methanol is what's called wood alcohol. Like if you were to ferment wood, you would get methanol instead of ethanol, because there's not as much sugar content in wood as it is corn or wheat or potatoes or whatever else you might want to make it from. When I was in high school, my chemistry teacher, when we were talking about this kind of stuff, he taught us like what kind of fruits or vegetables you had to ferment in order to make a particular type of alcohol. And it's like everybody paid attention for that part, you know. Even the guys in the back that are like just a complete waste, they were like, oh, yeah, man, potatoes make vodka, okay, you know, and they get all excited over it. So that was, you know, practical applications of things there. So watch out for those guys. Oh, coincidentally along that, of course, I was still teaching high school chemistry when Breaking Bad came out. I had a lot of students who were like, Mr. Hurt, that guy Walter White reminds me of you. And I was like, oh, you know, and I'm very involved in my church, and that was on Wednesday nights or Sunday nights, I forget. But anyway, it was at church, so I could never watch Breaking Bad. So then it came out on Netflix, and I was like, oh, look, you know, let's see what Breaking Bad is. All my students always said he reminded me of them. And I watched the first episode, and I was like, oh my goodness. They think that I'm this? What is wrong? So see, you miss out on that kind of stuff when you're just doing a virtual lecture. Okay. All right, so we talked about that, polarity, we talked about hydrogen bonding. I'm really hitting the points that you really need to know. You know, I'm a conceptual teacher, so you got to watch out because sometimes I don't talk about the definitions of things because I think of it as how it works rather than the name of it. So you got to watch out for me because there may be something that pops up and you're like, when you're reading a problem, you're going to say, well, he never talked about whatever. Well, lots of times I talk about it, I just never name it because that's not how I don't process things that way. So kind of a learning disability, not really, but I wouldn't say that. I just don't think that way. So some people will give you a sheet, some college instructors, and this is disappointing, they'll give you a sheet of definitions and be all like, match the words. I'm like, well, that's pointless, you know, unless you're just going to have conversations about this kind of stuff. I never talk to anybody about organic chemistry. I just understand how it works, you know. So you got to watch out for me. I had a calculus student that came back from her first year as a freshman, and she was taking calculus in college, and she said, Mr. Hurt, you never taught us about eigenvalues. And I was like, oh, yeah, I did. and then I explained to her what it was. She's like, yeah, I remember you going over that. And I said, yeah, I just don't call it that because I just never called it by name. I just said, this is how you work this type of problem. So I'm sorry. You have to learn some definitions on your own, perhaps. All right, we need to talk about acids and bases, and then I'm going to... Oh, we got exactly not enough time to do acids and bases. But we've got acids. And I do not know, last year's book, I used the 8th edition, I guess. Like, this chapter, when you read the title of this chapter, it says acids, bases, and structures. Organic structures, right? There's something like that. I'm like, these don't all go together. I don't understand why. And because last year, acids and bases were a completely different thing. And then they realized that they didn't cover, I guess they realized that, like back in chapter 2, they expected us to just know all these functional groups, because that's the last part of it is functional groups. And so chapter 3, we start talking about functional groups, and the students were like, what are you talking about? So when I did this over the summer, what I did was I took chapter 1 and then chapter 2, which was about the acids and bases, and then I did chapter 3. In between 2 and 3, I did my own chapter on functional groups and naming and how to draw things. And then I guess the book authors realized we don't explain this early enough. We just expect everybody to know it. So anyway, so now we're actually getting into the part that would be chapter 2 from the old book. All right, there's 3 different types of acids and bases, okay? And these are things that you need to know because they're going to come up conversationally, and I'm going to say it. And so you'll have to know these. And I just said I'm not really big on definitions, and I'm not. I'm bigger on people and understanding what these people did. But the first one is called an Arrhenius acid. And I never do spell that right. Arrhenius. I think. Well, we'll go with that. You can laugh at me when you're watching this later. Arrhenius acids and bases. Okay. They are Arrhenius acids and bases. There was this guy, his name was Svante, Svante, Svante Arrhenius. And he was doing his research as a graduate student. Well, actually, and he's going for his PhD in chemistry. And he came up with this idea of how acids and bases worked. Because they knew that there were things as acids, and they knew there were things as bases, but they didn't really understand how they worked. So Svante Arrhenius said, this is what they are. He said, an acid releases, that's a better word to say it, a hydrogen ion in solution. And so he explained that, and he said, this is how it works. Well, his graduate professors were like, oh, Svante, you're such a fool. This is not how it works. We don't believe you. And so we're going to do worse than failing you, because you're like, what could possibly be worse than failing you? It's shaming you. So instead of failing him and allowing, because if you failed, you got a chance to make up your work and try to recuperate, right? But instead, they gave him the equivalent of a D. It's like, you passed, but you stunk at it, basically. And it sort of stuck him where anywhere he went and he applied to try to teach or to whatever, do research and all, they looked at it and they said, you got this D? It basically says that you're a minimum achiever and you're never going to accomplish anything. And so it kind of ruined his career. And then like 8 years later, he got the Nobel Prize for it. So it's pretty awesome because it actually worked out. Acids release a hydrogen ion in solution. Okay, that's basically the key to it. He said the bases are going to have a release of a hydroxide ion in solution. Now, and that works out because especially when you're looking at your general chemistry stuff, we can classify things as acids and bases, H2SO4, and we can have NaOH, and we can have MgOH2. Oh, I put my parentheses in the wrong place. I have to fix that. And we can have like HC2H3O2. And so in general chemistry, it was really easy for us to identify acids and bases by just looking at them and looking at the structure. And so you look at that structure, each one of these starts with a hydrogen. So it's going, when you put it in water, it's going to be a acid. And each one of these ends with a hydroxide. So we put that in water and it's going to be a base. Pretty simple, pretty straightforward, easy to understand. But there's a problem with that. You know what the problem was? Ammonia, NH3. All right, so acids and bases have been characterized, and they said, okay, well, acids will turn blue litmus red, and bases will turn red litmus blue. And that's how the standard of figuring out whether it's an acid or a base was. If it turned it red, it was an acid. If it turned it blue, it was a base. Now, here's the fun thing about that. Fruits work this way. You ever eat a green tomato raw? They're unbelievably bitter because they're green, and that is an acid-base indicator. Raw green tomatoes are really bitter because they're basic. When they turn red, you know, tomatoes are one of the most acidic fruits out there. When they turn red, they essentially, that's your litmus paper. And it's saying, oh, it's red now. It's an acid. And it's okay to eat. I think that's so cool. So, problem with ammonia is a gas. And when you put that in water, you get it as a base. What's wrong? Bases release hydroxide ion in solution. These had hydroxide ions. There is no hydroxide ion on that one. So there's these two other guys who are competing for this, and they did this at the same time, Bronsted and Lowry. And they came up with this theory at the same time. Bronsted was like Swedish, maybe? I don't know. He was not English. Lowry was English. Okay, so when it first came out, they gave Lowry all the credit. They're like, oh, because you know how the British guys are. They're all like, very good, well, good job, sir. Hero, you know, or whatever. And so they came up with this idea that acids are hydrogen donors and bases are hydrogen acceptors. Acceptor, OR or ER? OR, right? Acids are hydrogen donors. Bases are hydrogen acceptors. All right, so let's look at ammonia and see how this applies. So ammonia, I'm going to draw the Lewis structure here. Oh, we should all do it, or whatever. You should watch me do it, or at least something. So we have ammonia's NH3, correct? Nitrogen has how many valence electrons? 5 valence electrons. Hydrogen, of course, if you don't know it has 1, you might want to retake this class next year. And so we add that together and we wind up with 8 electrons, right? Okay, 8 electrons. Which one's going to go in the center? Nitrogen. And then we know it's going to have at least 1 bond to each hydrogen. So how many electrons did that use up? 6 electrons. So we're left with 2 electrons. Well, hydrogen is happy with 2, so we don't need to add any to the hydrogens, but nitrogen needs 8. So where are we going to put the other 2 electrons? We're going to put them right on the top of the nitrogen, just right there. All right, now, whoops. If I hold my pen down, it turns into a selector because I drew this in the wrong place. See, I can do this, but you can't when you're writing on paper. It's not really fair, is it? So we have water comes into this. We put this in water, and it can actually, it doesn't have to be in water as a solution. It could be the water vapor from the air. Okay? What do we have that can take place here? Hydrogen bonding. And that's exactly what takes place. This hydrogen gets attracted in, and it attaches to the lone pair of electrons on the nitrogen. And then when that takes place, it actually loses contact with the oxygen from the water. And so we wind up with this creature here, which is going to be N, H, 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 and another H here, NH4. And that is the ammonium ion. Because when it grabs that hydrogen, remember hydrogen is a proton, and protons have what charge? Plus. So this thing has a positive charge. And when we draw a Lewis structure and we put big brackets around it and positive, we know that this is a charged molecule. This is actually an ion at this point, a polyatomic ion, the ammonium ion. And then the other side of it, we have another polyatomic ion. When the hydrogen leaves from here, it doesn't get to take the electrons. The electrons stay on the oxygen. And so over here, the oxygen winds up with 6 lone pairs of electrons. Anytime you see oxygen with 6 lone pairs, 3 lone pairs, 6 non-bonding electrons, you know that that oxygen has a charge of -1. And so this is our hydroxide. And so we have ammonium and hydroxide. So ammonia gas, when it comes in contact with water, hydrogen bonds, pulls the hydrogen off, creates an ammonium ion, and then it also leaves us with a hydroxide for the other part of it. So this is a balanced equation when you add those two together. And we get ammonium ion and hydroxide ion. So what does that mean? Well, let's look back over here and think about it. I'm going to draw this out as a reaction equation. NH3 plus H2O yields, and this is a weak base. It stinks. I mean, it's really strong and pungent, but it is a weak base, and it's ammonium hydroxide, NH4OH. Okay? And this is made up of course, NH4 with a positive charge and hydroxide with a negative charge because it's in solution and it's soluble. So what does that mean? Why did I draw that over here? Well, that's because something in this reaction took a hydrogen. What took a hydrogen? The ammonia did. So this is a base. Okay? Something in this reaction gave a hydrogen. The water did. So this is the acid. So did you know that water was acidic? It was actually both at the same time. And over here we wound up with these 2 ions that are in solution, the ammonium ion and the hydroxide ion. So this is the conjugate acid. Got it backwards. That's the conjugate acid, and this is the conjugate, right. And that's the way that works out. Whatever takes the hydrogen is the whatever takes the hydrogen is the base, whatever gives the hydrogen is the acid. And that's the way that works. That's the Bronsted-Lowry definition of an acid and a base. But that's not good enough, because there's actually acids and bases that don't even have to have hydrogen in them. And that's where you get into the organic chemistry stuff. These are far less common. Okay. Now, I have to remember Lewis acid takes a pair of electrons. Because, like I said, when it's talking about definitions, this is where I don't excel at definitions. So I have to think about a practical application of this. And I'm thinking, okay, boron trihydride is a Lewis acid. Right? AlCl3 is a Lewis acid. No, AlCl3 is a Lewis acid. Boron trihydride is a Lewis base. Okay. All right, so here we go. If I get this wrong, so help me. I guess I should look it up, right? Maybe I should. Because I don't want to lose all of my credibility on the first time you ever met me, right? Let's see. Lewis bases have available electrons that can be donated. Lewis acids have speed that can accept the electron. Oh, I got it backwards. I knew I would. Lewis acids give electron pairs. And Lewis bases take electron pairs. Double check that. Electrophile and nucleophile. Yep. Electrophile is an acid. Electrophile is an acid. Okay. Electrophile is an acid. No, that's backwards. I knew it. Electrophile is an acid. See how it's just this part.
So it's not like Bronsted? Okay.
Yeah. It's the opposite. Lewis acids take electron pairs. I don't ever use the words when I'm working a problem. Lewis acid accepts a pair of electrons. It's an electrophile. Okay. Takes an electron pair. Okay. Lewis acids take an electron pair. Lewis acids. See, you know why I'm saying this over and over again? Trying to remember it. Because somebody's going to ask me later and I'm going to not know what I'm talking about. All right. Lewis acids. I always get these backwards. Okay. All right, so we got this creature comes up in here. NH3 and BH3. The electrophile takes the electrons. It is the acid. Okay. Takes the electron, it's the acid. All right. Well, these actually will bond together. And they will make this. H3 and BH3. Okay. One of these is a Lewis acid, and the other one is Lewis base. And you know what? We're going to find this out together because I know how it works. I just can't think of it. I'm not good with the terminology. All right, so I'm going to draw my ammonia again. Remember this from earlier? Okay. Lone pair of electrons on a nitrogen. All right. Boron trihydride. Remember boron's special? It only needs 6. And that's a poorly drawn molecule, but we'll work with it. Okay. What happens when these two come in contact together is the electron pair and the nitrogen will actually move to the boron, and they will bond together, and they can make this creature over here. So the nitrogen is donating a pair of electrons, and so it is a Lewis base. And then the boron is taking a pair of electrons, so it's a Lewis acid. And then they bond together as a result of that. Now, this has very limited practical use for actual reactions. Okay. Typically, what happens with the Lewis acid and the Lewis base is they are used as catalysts. They will make an organic reaction take place. So to learn this and be like, oh, this is a Lewis acid base reaction, it's not really. And that's why I kept saying, you heard me saying electrophile and nucleophile. That's what we look at more than anything, is we will look at it whether it's an electrophile or a nucleophile. And so in this case, we'll see that this is a nucleophile. Okay, what does that word mean, nucleophile? What does the word, I mean, it's Greek, right? Nucleo is the nucleus, the central part, and phile means lover of. This is a nucleus lover. And then we have this boron over here, which is an electrophile. And this is the term that we will use more often, is nucleophile and electrophile. We won't typically say, that's why I'm having such a problem with Lewis acid and base, because I never say it's a Lewis acid, it's a Lewis base. I'm always going to say it's an electrophile, it's a nucleophile. And so this is the more common terminology of the nucleophile and electrophile. If it's an electrophile, it loves what? Electrons. It loves electrons. And so that's the key point to pull away from that, is knowing that the electrophile and the nucleophile, not necessarily the names of acids being Lewis acids and Lewis bases, but more about the relationship in between them. One of them loves electrons, one of them loves nucleuses, and that's what we have there. So we've gotten down to Lewis acids and bases. Anytime you see a compound that has an open area where it can take a negative charge, that's going to be, that's shining in my eye, an open area where it can take a negative charge, that's going to be your electrophile. So if we had, let's go with another one that's a little more, let's say this HSO4 with a negative charge. When you see a compound like this, HSO4, this is an ion, and it has this negative charge, is this going to be a nucleophile or an electrophile? It's going to be a nucleophile. Why? It already has a negative charge. It already has enough electrons, you see? So this is a nucleophile. And this is far more important to grab it this way and say, oh, well, this is actually a pretty easy understanding. And so if you had another compound in here that had, let's say, I'm trying to think of a good one that's, okay, CH3Li with a positive charge. Okay, and so in this case, we have this positive charge, and that's going to be an electrophile because opposites attract. And this is methyl lithium. Methyl and lithium, methyl lithium. This is a amazingly reactive substance. It's used in a lot of organic chemistry because it's so crazy reactive. Okay, so nucleophile, electrophile, that's where Lewis is at. So there's very likely, after today, you may never hear me say Lewis acid and Lewis base, because I always refer to them as electrophiles and nucleophiles because that's functional to me. Saying that Lewis did it, I don't care. I mean, I don't know what the guy's, I could care less what the guy's name is. So I'm more concerned about, can you identify it and use it if you need to. Okay, now I'm not going to, I've assigned problems in chapter 2 on Canvas. Okay, as part of the, I'm going to stop the recording at this point. Wow, I talked a long time.